Hello everyone, my name is Yuval, and this presentation is the first part out of two presentations where we are going to show you how reinforcement learning can be used to optimize single and two-qubit gates on real quantum hardware without having any prior knowledge of the underlying model. When we think about the future of quantum computation, a clear end goal is to be able to run algorithms that solve meaningful problems. In order to achieve that, we must be able to execute high-quality gates, which require a high level of control and optimization. So why are we interested in reinforcement learning? That's because the widely used model-based methods struggle on real devices. Unlike in simulations where model-based methods are successful, on a real hardware, it's much harder to accurately estimate the model parameters. There are unwanted effects like crosstalk. There are noise sources that are often uncharacterized, and parameters tend to drift over time. All these render the task of model-based learning extremely difficult on real hardware. This is demonstrated in the plot. You can see here the evolution of the qubits population in the presence of a drive. The solid lines are calculated from a simulation that assumes a model taken from the IBM backend, and the dots are data points taken from the real device. The exact details are not very important, but you can see clear discrepancies between the data and the simulation. The question that we want to answer today is, can we learn gate implementations without having any physical model of the system? Let's see a simple demonstration of the capabilities of reinforcement learning. Here you can see a reinforcement learning controller that was trained to complete a Rubik's Cube with a robotic hand. I won't show you the full movie, but during this movie, this poor robotic hand suffers many disturbances. Its fingers are tied, it is covered by a rubber glove, and at some point it is even attacked by a stuffed giraffe. And yet, in the end, it achieves its goal. We show here that reinforcement learning can provide similar benefits also to the control of noisy quantum computers. Reinforcement learning is a type of a black box optimization technique, and it is based on the idea of improving by interacting with the system, as described in this chart. We can represent gates by long vectors that, for example, store the real and imaginary part in each segment of a piecewise constant pulse. We then send the candidate gate to the device and evaluate its performance by collecting measurements and calculating a cost function. We then use that information in order to suggest a better candidate. This loop goes on until we find a satisfactory gate implementation. Unlike in many other black box methods, reinforcement learning also gathers intermediate information in order to build an internal model of the system. Let's quickly go over the basic steps of reinforcement learning. In each step, as seen in box A, we use the most recent observation of the system in order to choose the next action. In this case, an action can be two values for the amplitude and the phase of the pulse in the next segment. An action can also be the values of the pulse in several segments, and in general, the number of segments in an action is a hyperparameter of the model. We keep building the pulse step by step, and while doing so, collecting information about the state of the system after each step. A sequence of steps that form a full gate is an episode, as seen in box B. Once we have a full episode, we want to evaluate its performance. For that, as seen in box C, we run it in full and collect measurements in order to estimate the state of the system. Finally, as seen in box D, in order to wait out state preparation and measurement errors, and in order to uniquely define the gate, we repeat the full gate a different number of times and calculate the fidelity with respect to the ideal target state in each case. The reward that we assign to a specific gate implementation is then a function of these different fidelities, and this is the quantity that we wish to maximize. I don't have time in this talk to cover the theory of different reinforcement learning algorithms. I'll just say that we explore different algorithms, among others, the ones that you can see in this list. Now we are going to explore the optimization of a single qubit gate. The gate that we choose to work with is the RX90. It's a very basic gate, and any single qubit rotation can be generated using RX90 and Z rotations, which on the IBM device are virtual and therefore ideal gates. The IBM default RX90 is a 36 nanosecond drag pulse that is calibrated on a daily basis. For those of you who are not familiar with the drag scheme, the idea there is to reduce leakage to higher levels outside of the computational space. Leakage is typically one of the main obstacles in achieving shorter gates. Unlike with 2-qubit gates, the performance of the default RX90 is not far from the T1 limit. So what can be improved? We can still achieve some improvement in the performance and make it even closer to the T1 limit. We can also look for shorter pulses without degrading the performance, and we can also look for robustness over time, which may obviate the need in daily calibrations. Here you can see the progress of the optimization process on the IBM device Rome. Our starting point is a random pulse. The plot shows the mean fidelity versus the reinforcement learning step. When we are satisfied with the fidelity value, we take the final pulse and test it against the IBM default pulse using randomized benchmarking. On the left, you can see a randomized benchmarking experiment done with the IBM default RX90 and a 29 nanosecond Q-control optimized pulse of RX90. As you can see, even though the Q-control pulse is 20% shorter and should be affected more by leakage, its performance is more than 20% better. On the right, you can see the I and the Q components of the optimized and the default pulses. We can even go shorter, up to 12 nanosecond pulses, meaning 3 times shorter than the IBM default. For these short pulses, as we'll see in the next slide, we can achieve similar performance to the IBM default pulse. Remember that the IBM default is recalibrated on a daily basis. Here you can see the errors as calculated from randomized benchmarking across many days. For this, we always use the same Q-control optimized RX90 as we find in day 0 and compare it to the most updated, daily calibrated IBM default. As you can see, both with the 29 and 12 nanosecond pulses, we can achieve similar or better performance than the IBM default on a scale of many days without recalibrating. So what's next? In the next talk of this session, Mirko will show us an improvement of more than 2x that can be achieved with 2-qubit gates, which in general pose a much bigger challenge on real hardware compared to single-qubit gates. On top of that, our next step is to go beyond gates and use reinforcement learning and other black box optimization methods in order to improve the performance of small-scale algorithms on real hardware. That's all for me. Please stay tuned for the next presentation. Bye-bye.